Hi everyone, today we're going to talk about forces on slopes. We're going to talk about situations where those forces are balanced and situations where those forces are unbalanced. So we'll start with the forces that we know we've got. And a nice pink colour. The first one we know we've got is the weight of the box. If it is on Earth, then it's mass times gravitational field strength. We know that gravitational field strength at the surface and around the surface of the Earth is 9.81, more or less. Then we know that it's also got a reaction force to the surface. We call that normal reaction force, and it's normal because it's always at right angles to the surface. Let's talk about balance forces first. So let's change the colour pen and let's talk about the forces that are keeping my box from sliding down the slope. So the force that's keeping my box from sliding down the slope is friction. Maybe I should label these. Let's label these in a different colour as well. So this one down here, that's the weight of the box. This one up here is the normal reaction force. And then this one up here is friction. So in my world of balanced forces, I want to find out how big the friction is, how big the normal reaction force is. But in order to do that, I want to resolve all of my forces into the direction of the frictional force and the direction of the normal reaction force. So what I can do with my weight is at any time I can choose two perpendicular directions to resolve my weight into. And in this case, it makes sense for us to resolve my weight into the same directions as R and friction. In my head, I would be moving that the component of the weight which is parallel to the slope. I'll be moving that down there to make this a right angle triangle, so that I could do my trigonometry that we talked about in the last video, and I can make sense of that. The other thing that I need to know, and that I would know probably, is that this angle down here is theta. Now I can figure out what's going on with the angles in my triangle, because if I continue that line down there and I've got an angle there, then I've got an angle up here of 90 minus theta, and that's opposite that angle in there. And then I've got a right angle in there, which means that if I've got a right angle in the right hand corner and 90 minus theta in the bottom left corner, then the top angle there, if I get rid of, I'm going to get rid of that one. I'm not going to do it. This angle in here is theta. So if I take that triangle out, I know that I've got my weight down, and then I've got a component there, and I've got a component there. This angle in here is theta. I can use my trigonometry, so this, the bottom side is going to be mg, which is my hypotenuse, times sine theta, because this is my opposite side, so sine theta is opposite over hypotenuse. So I can multiply both sides by the hypotenuse to get that. And then the other side would be mg cos theta. So now I can add those magnitudes on here. mg cos theta and mg sine theta. So then in equilibrium, so this is proper equilibrium. So this is both translational and rotational equilibrium. We're not talking too much about rotational right now. A frictional force equals mg sine theta, and then R, the normal reaction force, equals mg cosine theta. Remember, in equilibrium means at constant speed. In fact, it's better than that. It means at constant velocity. And that includes 0 meters per second. So it includes but isn't exclusive to not moving. It could be going at a constant velocity. So my other situation is where it's not in equilibrium. I mean, the chances are it's not going to be moving away from or into the slope. So chances are R still equals mg cos theta, but it's likely that if I've got an acceleration, if we treat, so in this case, it's almost certain that it's going to slide down the slope if it's not in equilibrium, unless it was going up the slope and slowing down, but it's likely that the acceleration is going down the slope. So let's make that direction positive. And let's say mg sine theta minus the frictional force would give me the mass times by the acceleration. So that would be what we can call F net, the resultant force, or the net force, the sum of all the forces acting in that direction. Again, we can treat all of our components that are perpendicular to each other independently. So the R, the normal reaction force, and mg cos theta doesn't affect our frictional force and our mg sine theta and our ma. That's not entirely true, what I just said, but for A-level physics with AQA, we don't talk about actually what is friction. Feel free to look that up. So that gives us equations for forces on slopes for a mass, which is either in equilibrium, so it's at a constant velocity or zero velocity, and not in equilibrium, so it's accelerating. We could also have a situation where, let's add in brackets, so if this was a powered thing, like a car, if we add in FE, and again I'll label that one as a engine force or engine / driving force. We could add that one in, depending on which way the driving force it was. So in the context here, I've got the driving force driving down the slope in the same direction as mg sine theta, but there's no reason why it couldn't be acting up the slope if it was acting up the slope, but mg sine theta was still bigger, then we'd still have friction opposing the direction of motion. So friction's always in the direction to oppose motion or to oppose intended motion. Thank you very much, and I'll see you all soon.